So let's continue with our lecture. So what we are doing now, or what we are dealing with at the moment, so we are in the stream 19. So these are the some conditions. Like our stream 19 is at 20 degrees centigrade and at a pressure of 15 atmosphere. That's the current molar flow rate. And this stream comes from stream 18. So this is the stream which comes out of the pyrolysis chamber, which should be at a really very high temperature, 550 degrees centigrade, and at a pressure of 30 atmospheres. So we need to quench the temperature of the stream in order to avoid degradation of the product, and also in order to avoid the complete carbonization of the product. Yeah. So that's the, and also to stop the reaction. That's another main purpose. So I added like a cooler, and then we reduced the temperature from 550 degrees centigrade to straight away to 20 degrees centigrade, and to we also reduce the pressure from 30 atmospheres to 15 atmospheres. Okay, so maybe I will give you a quick summary of what we did so far. So let me zoom out the screen. So I hope you all remember what we did until now. So, so let's go through quickly. So we did some like a direct chlorination reaction where we mixed ethylene with the chlorine atom, chlor- chlorine molecules, and then we try to produce uh, ethylene dichloride via direct chlorination, and obviously we have to mix these streams, and then we maintain some particular temperature, and then before I use the continuous stirred tank reactor, I also showed you how to add the reaction site and so on. However, um, it doesn't work for us. Yeah, so we found there was no product formation from the CSTR tank, so I replaced it with a conversion reactor. So you have to check the literature 3 to know what we are talking about at the moment. And then we are also manufacturing ethylene dichloride from oxychlorination process. Obviously for that we need hydrochloric acid, we need oxygen, and then we also need ethylene. And then obviously we have to maintain some temperature, we have to maintain some pressure. And then I modeled the catalytic reactor as a plug flow reactor. And then obviously I also showed you how to adjust the reaction time and so on. Yeah. So if you want, we can even check that. Just right click on the plug flow reactor. We can say show table. It will give you some other information like that's the reactor volume. If you want, we can even add, say, add variable. Uh, okay, I couldn't find the time. Okay, let's put time for a. Okay, there is. Okay, let's leave this one. So okay, anyway, you can see the reaction time here. If you double click on the spreadsheet, we maintain the reaction time of 9 E minus 002. That's the residence time, the plug flow reactor. And then we also use the set function in order to maintain the temperature which enters the catalytic reactor, and the temperature the stream that exits the catalytic reactor should be maintained at the same temperature. So which means we are maintaining the same temperature throughout the reactor. So that's the meaning of that. And then so we take ethylene dichloride from the direct chlorination, from the oxychlorination, and then we are trying to purify that material. So our aim was to get the 99.5% pure ethylene dichloride. So in fact, if you look at the mole fraction of ethylene dichloride, we have 35% purity. So we used a separator, component separator, followed by 5-stage liquid extractor in order to get okay, this component separator helps us to achieve 65% purity, followed by liquid extraction in order to reach 92% pure ethylene dichloride, and finally we use a reboiled absorber in order to achieve our the desired level of purity, which is around 99.6 percentage. This process I also showed you how to model these unit operations using Aspen HYSYS. Obviously, we also have several minor unit operation, in this case like a heater, and then sometimes we use cooler, and then we are using some compressor and so on. And finally, the third step, which is the pyrolysis or thermal cracking of ethylene dichloride to vinyl chloride monomer. So we use we use the PFR in order to model the pyrolysis chamber, and then we also used again the spreadsheet. I showed you how to use the adjust key in order to maintain the residence time and also length to diameter of the plug flow reactor, the length to diameter ratio of the PFR unit, and so on. Yeah. So and then eventually we came here. This is our product stream. Our product stream should contain vinyl chloride, monomer, and also hydrochloric acid, and also some of the ethylene dichloride unreacted species, because we don't have 100% conversion here. So that's the so we are here at this stage, and then so we have to quench the temperature. So I reduced that, we used some cooler, and then in order to bring our temperature to 20 degrees centigrade. So if we click on this table, and then again we can check the molar fraction. So it should be the same, but still we can add a mole fraction. Okay, mole fraction. So master components, we can add vinyl chloride, we can add ethylene dichloride, we can add hydrochloric acid, we can even add water, probably it should contain some. So press done. So you have this, we have some trace quantities of water, and then mostly vinyl chloride monomer, and then HCl. So they are in the stoichiometric ratio, 0.4, 0.4, and then some unreacted ethylene dichloride. Okay. So what we need to do is we need to produce 100% or 99.5% pure vinyl chloride monomer. So we are going to use distillation in order to separate vinyl chloride monomer from the other three components. So how to do that? So before dealing with distillation, just if you look at the molar fraction, so we have different components: vinyl chloride monomer, ethylene dichloride, hydrochloric acid, and some water. So obviously we may need either one unit operation or more than one unit operation in order to get a pure product. Or even if you're using one unit operation, say distillation, probably we have to perform it in different stages. So we install a column to separate some component from the rest of the other components in the picture, and then we can use one more distillation column in order to get vinyl chloride monomer. So since we are dealing with really three different components, and two of them are impurities which we don't like to see in the final product, which will be vinyl chloride monomer. Yeah. So from the literature information, I already know that distillation works well in order to produce purified vinyl chloride monomer, but we have to give some justification. Yeah. So even in your final year design project, or even for the project which you're going to perform for this particular module, if you decide to use distillation, you have to give some suggestion, like or some justification, clear justification from purely chemical engineering point of view. Like why I decided to use a distillation column in order to produce 100% vinyl chloride monomer. So to do that, you have to pay attention to the fluid properties of each of these components. So let's stick to these three components: vinyl chloride monomer, ethylene dichloride, and hydrochloric acid. So the water is only in trace amount. So for the moment we ignore this. So let's check the fluid properties of these three components. So how to do that? Okay, before doing that, I hope you all know um, how distillation works. Yeah. So as a chemical engineer, you must know how the working principles of distillation, and how it allows to separate the our fluid components. Yeah. So you let's maybe I can use a PowerPoint. So you all know like different fluids. It's not writing. Let's say Okay, so just to follow the blue pen. Yeah, so we all know like different fluids boils at a different temperature. Yeah? So boils at a different temperature. Say like if you have a fluid mixture A, B, and C. So let's say we have a mixture of fluids A, B, and C. Say like if A boils at T1, say B boils at T2, and C boils at T3, and say like T1 is less than T2, T2 is less than T3. So obviously when we have a mixture, so if you supply a heat which is slightly equal to T1 or greater than T1, so only component A will start to vaporize here. So and then these two components will remain in the liquid phase, and these ones will start to, to vaporize. So depending on the temperature. So that's how the distillation works. So normally we have some fluid mixture. So based on the difference in the boiling point, we manage to separate one component as a vapor phase, and the remaining components which boils at a lower temperature, we collect them in the liquid phase, or something we can call it as a volatility. So it depends on the how volatility of the fluid. So volatility. So this term is inversely proportional to the boiling point. Yeah. To the boiling point. Yeah. So in fact we have to use other terminologies like bubble point, but we will come back to that. So what is that? So T1 it boils at very low temperature, which means T1 is highly volatile. Yeah, it's highly volatile, and T3 is less volatile when compared to T2, and T2 is less volatile when compared to T1. Yeah, so what we do is like so we mostly we collect the more volatile compound in the top, and then we collect the less volatile, or we can call them as a heavier components in the bottom. Normally we call them as light materials, and the heavier one comes in the bottoms. So that's the working principles of principle of distillation. Yeah? So obviously distillation is a very big topic. You can we even have several handbooks on distillation. So because and it's very difficult to cover this topic completely in this lecture. Yeah, at the moment we are learning to use Aspen HYSYS, and then we are going to use Aspen HYSYS to model the rigorous distillation column, and we are going to learn few tricks or maybe set of procedures that you need to follow while you are going to use Aspen HYSYS to design the distillation column. So we're just looking at some fundamentals before going into the full details. So far so good, I think. So let's give some numbers. Say like so so this one and your volatility will vary exactly opposite. So what does that mean? Like if you say fluid A, B, and C, and let's make a plot of say like a boiling point. Say T1, T2, T3. So the ratio so the relationship will be something like that. So this is, and in terms of volatility, it will be roughly 1 by T1, 1 by T2, 1 by T3. Yeah. So volatility. Say T1 is equal to 10 degree, T2 is equal to 20, T3 is equal to 30. So if you take the inverse, so this will be 0.1, 0.05, probably 0.033, not sure. Yeah? So which means the volatility is so if you express in terms of boiling point, it will be like this. If you express in terms of volatility, so let's call alpha 1, alpha 2, alpha 3. So alpha 1 will be greater, alpha 2 and alpha 3. Yeah. So this is less volatile, and your compound A is more volatile, and they boil at much lower temperature. So these are the things you should know. Yeah. If you have a fluid mixture in this case, let's go to the next end of slideshow. Okay. So in this case, we have a hydrochloric acid. Yeah, follow the red pen. So we have hydrochloric acid, we have ethylene dichloride, and then we have vinyl chloride monomers. So we have to separate them, and then we have to check which component boils at a much lower temperature. Yeah. So in fact, in a distillation, we have to check the bubble point. So this is something like, say, imagine you have this fluid mixture, HCl, ethylene dichloride, vinyl chloride monomer. So once you heat at, say, let's maintain the pressure is constant, and then once you heat the fluid mixture, the temperature at which you see the first bubble, so that's something we call it as bubble point. And then once you raise the temperature, obviously the vapor fraction will increase. Vapor fraction of that particular compound, say like if HCl boils first, so that the first bubble will correspond to HCl, and then your HCl concentration in the vapor phase will only increase, while these two remaining compounds may stay in the liquid phase. Yeah? So depending on the bubble point of these two other components, EDC and vinyl chloride monomer. So we have to check. Say we have say we have some pressure on the x-axis, and let's say we have some bubble point on the y-axis. Yeah? So bubble point. So what we are learning is we are learning some basics. Knowledge that we need to have before we touch Aspen HYSYS while modeling the distillation column, or if we decided to use distillation as a technique, then to separate some components from the fluid mixture, then we have to give some justification. So that's what we are learning. So what I plotted here, say like we have some plot like a pressure and as a bubble point. So remember, this bubble point also changes with the pressure. So if you fix the pressure to some other value, and then if you heat, then your bubble point may change. So 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 what you're going to do is we are going to plot pressure versus bubble point, and say component 1, say component 2, say component 3. This is temperature. A bubble point is temperature expressed, maybe we can use degree centigrade as our unit. Say pressure is expressed in atmosphere. So say this is for HCl, say this is for ethylene dichloride, say this is for vinyl chloride monomer. So clearly, say like you pick a pressure here and then draw a line. So obviously at this particular temperature, so only HCl will start to boil, and the remaining ethylene dichloride and vinyl chloride monomer, they will still remain in liquid until your temperature hit this particular point. For ethylene dichloride, and your temperature reach particular this temperature for vinyl chloride monomer. I hope you all follow up to this point. This is not a very difficult. Yeah, so it's really simple. So imagine we fix the pressure somewhere around here. Say pressure is say 20 atmosphere here. If you heat, you draw a line here. So your hydrochloric acid. So let me change the color maybe. Follow the blue color. So at this particular temperature, say T is equal to say T1, and above this temperature only HCl will boil until you reach this particular temperature. Yeah? So at this temperature your ethylene dichloride will start to boil, and at this particular temperature your vinyl chloride monomer will start to boil. Yeah? So 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 what we when we use distillation, we take our fluid mixture, and then let's try to maintain this particular condition. So this particular pressure and some temperature within this range, so that you can collect your hydrochloric acid, and then the remaining two components will stay in the bottom as a heavier components. Okay, because these are less volatile, your hydrochloric acid is more volatile. So we have to generate this type of graph. Aspen HYSYS can do that. So that's what I'm going to show you before we are going to design the distillation column. Yeah. So this is going to be a very long lecture. So if you feel tired, if you feel bored, you can you can pause the video from time to time, take a break, come back, continue listening, and so on. Yeah. So I'll try to upload this as one single video. But if you are really bored and if you think it's too much to listen, take a pause from time to time. Yeah. So nobody is going to to advise you when to stop. So if you think you need a break, pause the video, take a break, and then continue. So let's go back to our Aspen HYSYS window. So I'm going to keep all this PowerPoint, whatever I'm writing. I know this handwriting is not great, but I will upload this in the Sulis anyway. Yeah. So let's go back to our Aspen HYSYS. Before, let me check whether my microphone is recording my voice. Yes, it's doing well so far. So what we are going to do now, let's continue with Aspen HYSYS. So we have our at the moment I put some temperature of 20 degrees centigrade and pressure of 15 kilopascal. So let's keep this thing at the moment. So before doing anything with process simulations, let's calculate the fluid properties. So to do the fluid properties, it's very simple. So bring our palette back. So select your stream. So I'm going to add 3 streams for the moment. So this is like something like a temporary. Yeah? Just a double click. Let's add. Let's give a name. Let me call it as a HCl pure stream. Okay, and then this one 21. Let's call this as EDC pure stream. So at the moment we are trying to do something in order to justify distillation is a super good technique to separate or to get a purified vinyl chloride monomer. So let's call the VCM pure stream. Yeah? So we need to have some patience, and then let's fill the details. So I already said you in some lecture, like you have blue color, light blue, which means it needs some information. Once if the stream is fine, then we will get a dark blue color. The color changes. So double click, and then let's put some temperature. Okay, before that, I forgot to mention something. Okay, let's go back to the PowerPoint again. And then one thing you have to know, like say let's go back here. So something. So you should know what is a dew point pressure. Sorry, dew point and dew point and bubble point. Bubble point. Yeah. So something like imagine you have a fluid mixture A plus B. You're heating something, and then at some particular temperature, or maybe just have a pure component, say A. You just heat it. The first temperature where you see the bubble, the first bubble, this is called the bubble point. So at the bubble point, your vapor phase will be 0. It will start to increase from this stage. Yeah? So you, something like we're about to create the vapor phase. So at bubble point, that's the first bubble where you observe, your vapor phase will be equal to 0. And the same way, other way around. Let's say like imagine you have a component just full of gas molecules, so completely gas, no liquid in this, and this is the same component A. Let's say this is maintained at some very high temperature T2, and then if you decrease the temperature at which you first see the condensation, the very first liquid droplet, that's something we call it as a dew point. So at that stage, your vapor phase will be equal to 1, and then it's about to condense immediately. Okay, so that's the meaning. So at bubble point, your vapor phase will be equal to 0, and at the dew point will be exactly opposite. Your vapor phase will be at the maximum, say 1. After that, your fluid will start to condense. Yeah? So that's the difference between dew point and bubble point. So that's the take-home message. So dew point, your vapor phase will be equal to 1. Bubble point vapor phase is equal to 0. So this is some knowledge that you should have before we are going to do something with Aspen HYSYS. So let's keep it to my notes. Moving. Go back to this one. So what I'm going to do is I'm going to assume that I'm going to maintain my fluid stream at a bubble point. So to make that, all you need to enter is your vapor phase is 0. So which means you are setting our fluid stream to bubble point, okay? And then let's fix the temperature, or maybe let's fix the pressure. For example, let's put 1 atmosphere. Sorry, it should be one atmosphere, okay? 1 atmosphere, and then we have to give the composition. So this is a pure hydrochloric acid flows in the stream. So let's put 1. So I'm trying to check the fluid properties, okay? So that's why we are doing all these things. So unknown flow rate, let's give a flow rate of 100. So this number doesn't matter. We are just checking the fluid property. Yeah? So everything is converged. Green means everything okay. So what you see here, so automatically you see some number minus 84.78 degrees centigrade. So what does that mean? Hydrochloric acid, if your pressure is 101.3 kilopascal, then your bubble point temperature will be minus 84.78. So I hope you all follow this one. And then if you want, we can also calculate the dew point temperature the other way around. All you need to enter is substitute 1 here, and then we can calculate the dew point temperature. So I'm going to put 0. So this looks fine to me. Molar flow rate. Okay. So let me close this one. So what I'm doing now is, if you go back to our PowerPoint slide, I'm trying to generate this plot, pressure versus bubble point, to see that these fluids boil at a different temperatures. So based on the difference in their volatility, the level of how volatile these compounds, then I can say, okay, distillation is a good technique. So I can separate some components from the other components, and so on. Yeah. So that's what we are giving the justification using Aspen HYSYS, and we are learning that part. Okay. So you do the same for ethylene dichloride. So it's very simple. Vapor phase is 0. Temperature, I'm going to keep the pressure to 1 atmosphere again, like before. And then molar flow rate, I'm going to give 100. Let's go to composition, change ethylene dichloride, just 1. So only pure ethylene dichloride flows in the stream. So close this. Do the same for vinyl chloride monomer. So this is a good practice for you to know how to get the fluid properties. Okay. So you may need this later, maybe for some other module, especially for chemical engineering, thermodynamics. Yeah. So this is a good software to learn for many good reasons. Flow rate and composition, we will set vinyl chloride monomer to 1. So press OK. So far I'm happy with whatever we are doing now. So now what you're going to do, you're going to generate, say, such a graph, pressure versus bubble point, okay, bubble point temperature. So to do that, we have to do something, we call it as a case study. So let me close these things. So let's go back to home and press home and then click case studies. Okay, we have already a lot, we can delete them. So I'm going to create a new case study, press add, and then find variable. So you have to select the pure stream. So let's select a pure hydrochloric acid, HCl pure stream. and then let's select temperature. Mhm. Something is not working. Close this. Something is not correct. Case study. HCl pure stream. Okay, there is something with that stream. I'm not. Let me try with other one. Find variable EDC pure stream. What's the problem? Okay. Okay, let's put the pressure. Okay, pressure is good. Why audio is not detected? Okay, it's a recording anyway. So let's put pressure, and then we can change and then we can see how the bubble point temperature changes. Okay, close this one. This is done. Now this is for ethylene dichloride. Okay, find variable. Go back to ethylene dichloride, the same stream, pure stream, and then now check the bubble point pressure, which is here. Okay, bubble point pressure. Click this. Press done. Okay, go to case study setup. So let's do that. Go back here, and then you can change the units to atmosphere. Okay. Case study setup. Units are in atmosphere. So current value is at 1. So what I'm going to do is say like say from 1 atmosphere to 35 atmosphere. Step size of 1, and then press run. So it says success. So if you go to results, we get a plot of pressure versus bubble point. No, this is not something we want to do. This should be a linear plot. No, we have to go. No, go back to our case study. Find variables. EDC pure stream. Let's go to click the temperature. Close this. Press done. So delete this one. So click case study. Press run one more time. You get a result. Okay. So when your pressure is 1, your stream temperature is 229. Okay. 261. Let me check whether this makes any sense at all. Okay, Aspen HYSYS is a software, but still 35 to 50. Okay, this looks okay to me. So this is your bubble point temperature as a function of pressure, because we already said vapor phase is equal to 0. Yeah, so which means our stream is at bubble point. So let's copy this one. Go to our Excel sheet. So I'm going to generate something now. So click here, insert. So what we have here, we have pressure expressed in atmospheres with units, atmospheric units, and then bubble point temperature in degrees centigrade. Okay, so this is for our ethylene dichloride EDC. Okay, and then if you plot it, you'll get some graph like that. I hope you all will we'll do these things. Yeah? So don't skip the video. Do practice in the go to lab. Repeat everything step by step. Yeah? So don't even compensate on. Don't even think like okay, just I will skip and then I will go on. Try to do everything. A chart element, primary, horizontal, minor, vertical, blah blah blah. So this is for your ethylene dichloride. So let's do the same for the remaining two other fluids. So I know we are going a bit slow, but we are learning something very important in chemical engineering. So this is for ethylene dichloride. So we do that for vinyl chloride monomer now. Okay. So go to case studies, add a new case study this time, press find variable, select for your vinyl chloride monomer, VCM pure stream, select your bubble point pressure, done, find variable, go to vinyl chloride monomer stream, again, select temperature, select temperature, press done, and then do the case study again. Okay, change the units. It's better to stick to atmospheric units, so it will change here automatically. So what's meant by current value? Why it's not set? Current value is set to 101.3. Okay, case study 2. I hope I did correct. So VMC pure stream, bubble point. Okay, just put pressure maybe. Just put pressure. Okay, the current value is set. Close this. It's in atmospheres. Okay. Okay. Now you change the, say we start from 1 to 35 atmospheres. Okay. Step size of 1. So press run. So whatever the problems that I'm encountering, you will have the same issues when you are trying by yourself. Yeah. So trying to use the software by yourself. So pay attention to these details. So take these results. If you look at the plot, you have some result, something like at as a function of pressure, and that's your bubble point temperature. So take the results, copy it, go back to your Excel sheet, copy it here. Yeah, so this is same. Yeah, so this is your pressure in atmosphere and this is your bubble point temperature. Okay, and then let's do the same. This is for what? Vinyl chloride monomer. Let's do the same for hydrochloric acid now. Maybe I have to split the video into 2 or 3 because it's already, I'm talking for almost 40 minutes now. Yeah? So let's go to flow sheet. So let's create one more case study, this time for hydrochloric acid, pure hydrochloric acid stream. Click case study, add case study, find a variable. So go to HCl pure stream and then select pressure. So we are doing well at the moment. Yeah? So it's not bad. You're going a bit slow, but you're also learning a lot of things at the moment. Instead of learning Aspen HYSYS like a black box tool, you're applying some chemical engineering principles from time to time, and then learning and exploiting the software to purely as a chemical engineer rather than like I don't know. Hydrochloric acid pure stream, where is that? Okay, and then let's select the temperature. So good. So close this palette for the moment. Go to case study setup. Change the units to atmosphere. Pay attention to the units, okay, please. Okay, current value. Let's start from 1. End is at 35. Put step size of 1. All should be fine. Press run. Success. Very good. So results. So we can copy them. We can copy them and then we can paste it in the Excel sheet. So this is for our pure hydrochloric acid. And then I'm going to change this P and bubble point. I don't know. Let me see. Yeah. And now we can plot all the three. So what we have here. So what is this? Series 3 is HCl. And this is series 1 is ethylene dichloride. Series 1 is ethylene dichloride. Series 1 is ethylene dichloride. Okay. No, I think there is something not correct. No, series 1 is press cancel. So this is series HL.8. That's correct. This is a series 1. Series 1 is vinyl chloride monomer and series 2 is ethylene dichloride. Okay. So series 1 is vinyl chloride monomer and series 2 is ethylene dichloride. Yeah. Okay. So what we have here is something very important graph when we and what very important graph that we need when we think about designing the I don't know how to select this graph. Okay. Oh yeah. Okay. Couldn't select the plot. Okay. So let me add the chart elements to make it a bit more clear. So axis title. So what we have here is a pressure. Pressure expressed in atmospheres as a function of bubble point temperature. Okay. So this is such an important graph that we need, and you also learned how to generate or how to get the fluid properties from Aspen HYSYS. So this is something you learned through this lecture video. Okay. So what we have here. So at say like maybe I can copy paste in the PowerPoint and then I can explain. So what we have here is some graph of so what we have here, so we have some pressure and then bubble point temperature. So let's say like let's fix our fluid stream at say like 10 atmospheres for example, or maybe 15. How to do that? Okay, follow the light green color. Yeah? Okay. Let's say we fix the pressure at 15 atmosphere, which is this point. Okay. So which is at this point, and then at this point and at roughly at nearly 0 degree centigrade. So clearly your HCl is above the bubble point. Obviously, it will be in the vapor phase. The which mean in the vapor phase you will have only hydrochloric acid, and in the liquid phase we will have the remaining two other fluids. As so, this is your HCl. This is your vinyl chloride monomer. That's your ethylene dichloride. So at 15 at this particular pressure, vinyl chloride monomer may roughly, if it's a pure component, it will start to boil at this particular pressure around, I don't know, 50, 60, 70, 70 to 80 degrees centigrade. And then your ethylene dichloride will start to boil around 210 degree centigrade. So this is this is the case irrespective of the temperature. Say if you are maintaining a temperature of 5 atmosphere, your hydrochloric acid will start to boil even at lower temperature, okay, around minus 50 at cryogenic temperature. So definitely, and then if your temperature is above this value, obviously you will have high concentration of or hydrochloric acid in the vapor phase. Your vapor phase will contain only hydrochloric acid, and these remaining two components will be in the liquid phase. So this is one justification. So irrespective of the pressure, the boiling point, bubble point pressure, temperature differs for all the individual fluid components. So this is a clear justification to say that that's the reason I think a distillation is a very good idea to separate the fluid components. So I can take the fluid mixture, I can maintain some particular pressure, I can maintain some particular temperature where I can see only one component in the vapor phase, and then I will see the remaining components in the liquid phase. Okay, so that's the take home message. So this is the justification for this. And obviously, when you are going to deal with a fluid mixture, then this graph may change. Say, like if you have a mixture of vinyl chloride monomer and say like or all the three, then this curve may differ. Okay, so let's close this. So this is so we learned how to get the fluid properties using Aspen HYSYS, and we also provided some justification for using distillation column to separate the to get the pure phenyl chloride monomer. Okay, I think we've done the job, so I'm happy with whatever I explained so far. So I'm going to delete these things. So 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 just look at the anyway. We already have the chart, so we really don't need this thing. So we have to delete this individual streams. If not, we will have some problem later while we're going to develop the process flow sheet. So we already explained how to get the fluid stream. I pay attention in order to get the bubble point temperature. You have to set your vapor phase vapor fraction to 0. Okay, so which means your liquid phase will be automatically 1. So let's close this. So which means maximum liquid and your liquid is about to boil. Okay, that's the first bubble you see in the liquid. Close this, delete all these streams. So now we know we are good to go to separate these fluids using a distillation column. Yeah? So before explaining the distillation column, so let me add the distillation column, and you will see what what are the things we have to consider. So just a reminder, if this model palette, if it's disappeared, if you want to bring it back, you can press F4 in the keyboard. Yeah? I said this in the previous lecture, just repeating it so that if you forgot how to do that, just press F4. Okay, so if you put this, you will have so many icons, they all look like same, like brothers and sisters. So you have to check which one we need a distillation column. So it's here in the distillation column, it's placed next to expander. Click on the distillation column, select it. So once you double click, and then it will ask the first thing you will see inlet stage where it enters. Okay, so let's put so stream 19, that's the stream that we want to purify, and then it will ask some information where it enters. This is one information that we need, and also number of stages that we need to achieve the required level of separation. Let's put a total reflex, and then it asks for okay, let's give some name like a top. Let's put bottom, and then let's give some reboiler like a Q rib. So these are some random. Yeah? We will delete this anyway. I'm just showing what are the information it asks for. Q condenser. Okay, so let's put next. So pay attention. So what we need a inlet stage. We need to have some information about this, number of stages that we need, and then let's press next and press next. And then it also asks for what's the condenser pressure. So let's put 1 for the being. So this is I'm just showing what are the information we need in order to design the distillation column. Say reboiler pressure. It also asks for reboiler pressure. So press next. So I'm going to put some random temperature. Okay. So it's also asking for temperature in the top, which is temperature in the condenser, and it's also asking temperature in the reboiler. Okay. So temperature in the condenser, it means like whatever the whatever the component that goes inside, you should have some you should maintain some temperature in the condenser that should be enough to condense the gas back to liquid. So we will collect the, the top product as a liquid. Okay. So we need to, so what temperature we exactly need in order to condense that particular vapor that we comes through the top of the distillation column. Okay. And then what's the temperature we need to boil the fluid mixture in order to generate that vapor phase that allows the separation to happen in that distillation column. Okay, so these are the things that we need. So next, so liquid rate, we don't have to worry about this. We can fix some reflux rate, some ratio, say 3, 1.75 and so on. Okay, and then press done. So obviously there are few other things that we need to do. So what I'm going to do is I will close this. Okay, I will close this. Let's go to PowerPoint and let's summarize what are the things that we need. I think I'm going from top to bottom, which is a stupid way, but let me. You can restructure it. Yeah? So I will upload them in the Sulis anyway. So let's put it in the preview mode. I have to invest in some good pen, honestly, digital pen. What I have is utter shit. So let's go to the previous slide. So what we're having is so we we're taking stream 19 and we decided to use a distillation column. Okay, we have condenser, we have a reboiler, and we need to know. So the things that we need to know. Oh my god. Okay, so number of stage. Okay, that's one. The feed stage, where the feed enter. Okay, number two. So condenser temperature, very important. Condenser pressure, condenser pressure. Sorry, condenser. Sorry. A reboiler temperature, and more importantly, so we need to know that condenser temperature and reboiler temperature for some fixed pressure. So say our stream in the top is at some particular pressure, say P1 and some. So this is also again at P1 atmosphere. So at this particular pressure, what should be the reboiler temperature? That should be enough to create the vapor phase. And then what at particular pressure, what should be the condenser temperature? That should ensure that the vapor will be condensed back into liquid. Okay, so we need to know this temperature, and obviously we know the pressure, and and also these things vary as a function of your feed pressure and temperature. Okay. Feeling tired of recording this video. So these are the things we need, and obviously at the moment we know the fluid properties. We have it in the, and then we know like ethylene dichloride boil at very high temperature, vinyl chloride monomer somewhere in between hydrochloric acid and ethylene dichloride. Yeah? So we know the distillation works, and we need to know these values, how to get these values. That's what we are going to learn. Okay, and then we will also learn that depending on the feed conditions, these values will change. Okay, I will keep this. HYSYS. Let's go to one fresh, some new slide. I want to say a few more things about distillation. So when it comes to distillation, obviously it's a very very good unit operation. It's like a, let's change the color. Okay, I put this dark blue this time. Okay, so distillation is excellent if you have a fluid mixture with different boiling points. So based on their relative volatility, we can exploit that particular fluid property, and we can use the distillation column to separate them. But at industrial scale, what they think is it's very good to it's economical to operate your distillation with in the temperature that ranges from 25 to 186 degrees centigrade. Okay, so this is something like obviously we can go higher than this, and we can come lesser than this value. We can operate distillation column temperature less than 25, temperature greater than 186 degrees centigrade, but it is considered to be more economic to use this particular temperature. Okay, so why is that? Why is that? Because take a distillation column. Okay, I don't know how to draw this. I have to go some drawing class. This is a condenser. It's not about. I know my handwriting is bad, but not up this bad. This is my. I don't know how to write with a pad, yeah, digital pad. And then here we have a reboiler. So what I'm saying here, this optimal conditions. Say like this reboiler temperature. If there is a way we can maintain this temperature less than 186 and greater than 25, that means we are that's an we are in the how do you call we are in the economical distillation zone. Okay, economical distillation zone. And why is that? Because we can achieve this temperature 25 to 86 using simple steam, yeah, like medium to high pressure steam. Okay, you will not have a clue if you look at these things, but since I'm saying that and you are listening to my videos, you will know what I'm writing here. This is medium to high pressure steam. That's more than enough to give to to create such temperature. Okay, so 186 degrees centigrade. So if you use a high pressure steam, that's enough to create 186 degree centigrade of heat to boil your fluid mixture. Okay, in order to create what we want, some vapor phase which we need to collect in the top. And then the condenser, normally if you maintain some temperature around 25 degrees centigrade, say 25 to roughly I think, let me check my notes. I have typically condenser temperature we like to maintain. So this is your 25 to 86 is for your reboiler. Okay, so this 25 to 186 degrees centigrade, or just a, why this pen is disappearing. So we call this, or we can say like we are in the economical distillation zone if we maintain or if our reboiler temperature is typically less than 186 degrees centigrade, and then or 25 to 186, and our condenser temperature is typically in the range of 25 to 49 degree centigrade. So keep these things in the mind. So so reboiler, so less than 186, maybe 25 to 186, and then your condenser temperature should be 25 to 49. So if there is a way to do that, then we should be happy. If not, it's okay. Yeah? So, and why we call it as economical distillation zone is I already said. So we can use something like a medium to high pressure steam to maintain this, to create this temperature, and in order to boil the solution, and 25 to 49. So we can use a simple, not a normal river water, for example, river water or air cooling, in order to condense your vapor back to liquid. So that's why it's more economical to to maintain this temperature range in the condenser and also in the reboiler. Yeah? So whenever you are going to design a distillation column, so keep this temperature range in the mind and try to play with the process condition and check whether changing the this inlet temperature and pressure, something, if you change some values here, whether it allows you to to operate your distillation in the economical distillation zone. Okay, so let's do that using Aspen HYSYS. So this is something that you have to keep it in your mind before touching the software. So let's go back to Aspen HYSYS. Let me check whether I'm recording or not. Yes. So let's go back to the software. So so this is fine so far at the moment. So so we have the, if you go back to our slide, so we know what is economical distillation zone, some general idea, theoretical idea, and then we have some general idea about the fluid properties, and to have some what are the information that we need to design a distillation column. Yeah? So now we go to Aspen HYSYS. So what I'm going to do is, so let's close this. Let's close. Let's delete this distillation column. So this is not, we designed anything. So just I wanted to take a list. What are the information that we need in order to design the rigorous distillation column? Okay, so let me close this. So let's say we are maintaining the temperature of 20 degrees centigrade and 15 atmosphere, the exit stream. So so how to get the first information, say like our condenser temperature, and then our condenser reboiler temperature, and then if you go back to our PowerPoint, we already know by you can separate a hydrochloric acid. If you come back to this graph, say by, if our temperature is at 20 degrees centigrade, roughly around here, or maybe let's put the temperature to 10 degrees centigrade, or maybe even, so let's say our product stream is at 15, and then let's put our feed temperature to 20, and then let's see whether we can separate hydrochloric acid or not. Okay, so at the 20, okay, let's see that, come back to here. So let's say we are maintaining our temperature at 20, and then 1520. Let's go back to the fluid property. Okay, so let's do that. So to know what should be the condenser pressure, and for the case if HCl is going to be the product in the top and the remaining products will be in the bottom. So how to know that? So what I'm going to do now is, so so we have some mm, sorry, so we have some stream that goes inside. Okay, and then we need to know, and we know HCl comes in the top because that's a more volatile compound, and then the remaining less volatile heavy products will be in the bottom, vinyl chloride monomer and ethylene dichloride. So if this is the case, what should be the condenser pressure, and what should be the reboiler, sorry, condenser temperature, what should be the reboiler temperature? Okay, and then uh, okay, let's see that. Condenser temperature, reboiler temperature. Okay, let's see how to do that. Okay, so we are going to keep some, follow some set of procedures, try to take a note. So we have to call something called as, we have to add absorber component splitter. We have to use something called component splitter. So don't confuse with separator. It's called component splitter. So this is something like we are going to get some information that is record that information which are required to design the full distillation column. So at the moment we are taking the component splitter. So connect it to stream 19. Stream 19. Let's call the product stream, say some number 20. Bottoms out, let's say 21. So we have one product in the top, one product, some products in the bottom. Okay, bottom outlet, and then we are going to split them. So we are going to say like I am going to collect only hydrochloric acid in the top. So our top stream is 20. So let's put 1, and everything else are 0. Okay, so which means I'm going to collect in the bottom. Everything else should be, the remaining components will come in the bottom. Okay, okay, this is fine. And then now you go to parameters, put equalize all the stream pressures. So everything, whatever the pressure that goes to 19, that will be the same pressure in 20 and 21. We will check that later. Okay, using the something called as the show table option. And then let's say in stream 20, this is at your this is a bit tricky. Let me so what we are going to do is just using the component splitter, and we already fixed the temperature. Mhm. Then we have to fix the vapor fraction to 0. So why it's not working? So that's stream 20, which is in the top. So what we are going to do is so we are going to assume the distillate is at its bubble point, okay, in the top. So that's why you get something in the vapor phase. So it should be 0. So it's automatically solved. So what it says is like if you have to condense the, if you have to condense the fluid that comes in the top, then you have to maintain the condenser temperature to minus 18.89. Okay, let's close this, and then your reboiler temperature should be automatically equal to 57.88. Okay, so this is like a, these are some temporary information that we need. So let's take a, so let's add a table to this stream show table. Okay, so we have the pressure here, we have the temperature here, and then let's assume show table. Yes, okay, so we have to maintain the reboiler temperature of 57.88, and then a condenser temperature of minus 18.89, provided your pressure is at 15 atmosphere. So let's try to change the pressure and see what happens. Okay, or if you want, we can even make a case study. So what will happen if I change the pressure, and then so how the load in the condenser increase or decrease, or how the load in the reboiler increase or decrease. Okay, so let's try to do that. It's simple. Just select a case study, add, close this, and find variable, select stream 19. So let's change the pressure. Okay, let's change the pressure. Done. Change the unit to atmospheres, and then let's check the top product 20. let's say the temperature. Done. Okay, and then case study setup. Okay, the currently we are in 15 atmosphere, so let's start from 1 atmosphere to end value of what? Let's put 30. That's the maybe 25 atmospheres. Okay, and then put a step size of 1. Press enter, run it. Success. Go to results. Let's plot this one. Okay, copy these values, create a new sheet in the Excel, paste it. So I'm going to call this as a load in the condenser. Load in condenser. Time is the x-axis is pressure. Okay, so let's do the same again. Go to our, let's do one more case study. This time we will see the pressure in the stream 19 as a function of the temperature in the stream 21. Okay, which means the reboiler temperature. So go to case study. Case study, add a new case study, find variable stream 19. Let's select the pressure. Done. Find variable, go to the bottom product of the sub component splitter 21. Let's put temperature here. Press done. Okay, we should be happy with this value. I'm going to change the unit to atmosphere. Case study, let's start from 1 atmosphere to 25 atmosphere. Step size of 1. Press run. Check the results. Go to your Excel sheet. So I'm going to call this as a load in reboiler. Okay, so let's plot this value. So pressure of inlet stream. Okay, in atmosphere. So let's plot this too and see how it changes. Okay, so what we see here, so this is like exactly some opposite trend. So what we see here, so this is your let me copy paste it in a PowerPoint. Let me be easy to explain. So what we see here is we go to the preview mode. So what we see in this graph is so this is your the temperature in the your condenser temperature. This is your reboiler temp. Oops, yes, this is your reboiler temperature. So roughly they vary opposite the trend. So what it says, like if you spend more energy um, so what is this, minus 60. No, this is something funny. So this is something which I am not expecting. What's happening here? So at 5, the pressure is increasing. Then naturally you decrease the load in both in condenser and also in the reboiler. Okay, let's fix the temperature of say around this value, say like 15 atmosphere. If we fix that 15 atmosphere, then your condenser temperature is around minus 20 minus 20 degrees centigrade. It can be plus or minus some number, and then your reboiler temperature is around 60 degrees centigrade, which is not bad. So what we are going to select is so we are going to change the pressure of the inlet stream to 15 atmospheres. So it is already at 15 atmosphere, so which you're already in the good zone. Yeah, okay. And so let's stick to that. So let's go back, keep it. And if you see that, if you go back again here, so I don't know where is the mouse. So if you go back here, if you decrease the pressure, say like around 1 atmosphere, then you have to spend loads of energy to create a high temperature in the reboiler, and also to create a very low temperature in the condenser. Okay, so obviously this is not a good idea. So I think this particular zone is looks good to me. I don't want to come here. I don't know whether we can really manage to separate the fluid or not. So let's keep this zone in the mind. And so this is fine. So what we are going to fix now is temperature is at 20, which is already there, 20 degree, and then we already have the right level of the pressure we are maintaining at 15 atmosphere. But this graph will help you to know like how the how by simply changing I don't want to work with really compressed gas, so better 15 atmosphere is good. And then it's also temperature is moderate, 20 degrees centigrade, and it also requires uh, only around 60 degrees centigrade. This is a rough number. It will change once we add the distillation column in the reboiler, and then around minus 26 to in the condenser. Obviously we need to use some refrigerant instead of river water. So refrigerant instead of river water. Okay, so we need this the fluid in order to condense the streams. So keep these things in the mind. So let me press. So with this information, let's go back to Aspen HYSYS now. So we are already maintaining the 15 atmosphere and so on. And as I said, you can see if you, in the graph I showed roughly around 20. So the precise value is minus 18.89. That should be our condenser temperature, and this is roughly 60. I said in the graph you see here 15 atmosphere around 60. So the exact value is 57.88 degrees centigrade. Okay, so this is some information that we need to design the distillation column. So at the moment we are preparing the notes in order to design the distillation column, rigorous distillation column. So what I'm going to do is I'm going to take a snapshot, snipping tool. So let's take the snapshot of this one, what we have at the moment. So let's go back to PowerPoint. So let's paste this. So we got some information. So pay attention to these values here. Yeah? So this is your condenser temperature, reboiler temperature, and so on. So now we have to, if we come back to the slide here, so now we need to know the other values, number of stages, where where is our feed stage, where the feed enters and which stage, and then our condenser temperature we already have reboiler temperature, and we also know the pressure, which is 15 atmosphere. So let's try to get these informations, number of stage, feed stage, and so on. So let's go back to Aspen HYSYS. So just delete this unit, we don't need it anymore. Okay, and now go back to your palette, and now you have to set something for. So we are using the shortcut distillation method. You can do that theoretically, or we can use Aspen HYSYS, and it's called shortcut column. Just select, drag and drop here. Okay, just double click on it, select your feed stream is 19, and then let's call the distillate again 20, bottom say 21 again, uh, reboiler we can say q reb 1 maybe, condenser let's say q condenser 1, q cond 1. Okay, and then let's restructure it a bit. So if you see here, the stream comes out, which means we are going to take some temperature out, we are going to supply some temperature in. So that's the meaning of this arrows. And then what we have to do, pay attention. These are not, you may easily lose the track. And then a light key in the bottom. So what we are going to say, like if you come back to our PowerPoint, I said you in our case the light material is in our case is hydrochloric acid, and these two are our heavier components. So we have to say the light materials in the bottom is at minimum, and then the heavier components in the top is at minimum. Okay, so go back to our shortcut columns. Let's say light key in the bottoms, so or maybe heavy key, light key in the bottom. So hydrochloric acid, okay, is at 0.0001, so minimum in the bottom. Condenser pressure we know 15 atmosphere. Reboiler pressure we know 15 atmosphere. Reflex ratio we put 1.75 or maybe 3. Unknown key components, okay, user variables. Heavy key in the distillate, okay, sorry. Heavy key in the distillate. Vinyl chloride monomer. Say we have negligible amount of vinyl chloride monomer in the top, okay. So the stream is converged now. You can change the reflex ratio 1.75. Okay. So I think we got some information what we need. So if you double click the column now, or maybe you can just put like if you now we can check the new values for the condenser and the reboiler temperature. Right click, show table. Okay, it's 18.88, same value, around same value. Again, show table. Your reboiler temperature now is 94.62. So this is the correct value. Yeah? So obviously this number will change. So whatever we are doing is like we are using some different methods. Like we use the component splitter to get some initial values for the reboiler temperature, condenser temperature, and then we use that value to use it in the shortcut column, shortcut distillation column, and then we got some value for the reboiler temperature, and then some condenser temperature, which is minus 18.8. Okay, so normally in order to achieve this type of temperature, we like in the condenser, we in the industries they will use a refrigerated brine, and we can reach this temperature 94.62 with like medium pressure steam. That's more than enough to reach this temperature in the reboiler to supply this temperature in the reboiler, and we can use a refrigerated brine to maintain such a low temperature in the condenser. Okay, and then just right click on the column, press show table. So you will get some information about the table, like the minimum trace is 9, actual number of trace is 12. So this is some information we have to take. We need 12 or 13 trace, 12.49. So let's put 12 trace, and the feed enters in the trace 6, and then the minimum reflex is 0.3560. So these are some information that we need to design the distillation column. Okay, so I'm going to take a snapshot of the screen, this part, go back to our PowerPoint, go to our slide, and then let's paste it here. Okay. Let's paste it here. So what I'm going to do now, so let's put the highlighter. So we have this, this is our condenser temperature now. That's our reboiler temperature now. So that's our condenser pressure, reboiler pressure, condenser pressure, which is same as the feed pressure, 15 atmosphere. And then what else? And then we have these values. So the actual number of trays is 12, and then the feed stage is 6. Minimum reflex ratio is 0.3560. Okay, press escape. So with this information, we can go to the distillation column. We can add the distillation column. Okay. So let's close all this. Maybe let's delete the column. So we got all the information that we needed. So now it's time to add the distillation column. So click the distillation column, add it here. So add the stream 19. Okay, that's our stream 19. Inlet stage we already know, it's sixth tower. Number of stage is 12. So let's put the number of stage is 12. Okay, total reflex. Overhead liquid outlet, let's call it as HCl out, HCl out. And then in the bottom, let's say bottoms. Okay, or maybe, I don't know, let's call it stream 20, put it simple. And then let's call something like QReb 1, and then energy stream Q condenser 1. Energy stream, let's put Q condenser 1. This should be fine. Then press next. Press next. So we know what's our condenser pressure, which is 15 atmosphere. No, I think I did a mistake. It should be 15 atmosphere. And then our reboiler pressure is maintained at 15 atmospheres. Press next. And temperature we already know. Let's go to our PowerPoint. So it's minus 18.88 and then 94.62. 88 and then 94.62. Am I right? 94.62. So these are the information that we need and to design, and we also need something like the number of stage where the stage enters. This should be 6th tower, not 7. Press next. This is perfect. Next. Reflex ratio, I think I fixed it before to 1.75. Press done. So we are here. It says unconverged. So if you press run, you will see something funny. Yes. Distillate rate, and it's asking for a specific value. So what it says. Okay, to do that, because we need to add few other information. Distillate rate, we don't have it. So if you go here, you see here distillate rate, it's already checked in, and we don't know the rate. So let's uncheck this one, and then we also need to give some specifications like uh, what are the components of the hydrochloric acid in the top product. So let's put add spike, and then let's put column component fraction. I don't know, fraction or ratio. Let's try fraction, add spike, and then it's not stage, it's a stream. Target type is stream, and our target stream is HCl out. So draw HCl out at column 23, mole fraction, specific value, um, say 0.999. Which component that should come top? Hydrochloric acid. Okay, and then close it. Now we see it's converged. So what it says, what we did is like we set the condition so that we get hydrochloric acid in the top. So we can even check that. Right click, press show table, and then double click on the table, press add variable. Let's check the molar fraction of the hydrochloric acid. Master component hydrochloric acid. Press done. Yeah. You see 99% of is just hydrochloric acid. Yeah. So we separate uh, hydrochloric acid in the top, and we can check what's the thing in the bottom. Show table. Again double click, add variable, check the mole fraction components. Let's add ethylene dichloride, hydrochloric acid, vinyl chloride monomer. So done. So close this. So now we can see this our vinyl chloride monomer. It's slightly pure, more pure than before, 75% purity in terms of mole fraction. And if you compare it with stream 19, you can see it's only around 0.4304. Yeah, so it's not bad in time. So we managed to separate the hydrochloric acid out. Yeah? So probably we will recycle this hydrochloric acid, and then we will send this stream back into the process. Okay, so let's close this one. Let's close this. So I'm happy with this thing. So next we are going to add one more distillation column in order to separate your ethylene dichloride from this particular mixture. So that if you go back to our PowerPoint, if you look at the fluid properties, so ethylene dichloride, it's like is less volatile when you compare to vinyl chloride monomer. So we will find the conditions to take the vinyl chloride monomer in the top, and then the ethylene dichloride in the bottom. Yeah. So that's the deal. So and then we will try to do that at the same pressure, say 15 degrees centigrade, 15 atmosphere, sorry, the pressure, and then we will try to raise the temperature of the stream in order to raise the temperature of the reboiler in order to evaporate your vinyl chloride monomer, and then you will collect vinyl chloride monomer in the top. So if you look at this graph here for a bit, if you look at this graph, mm, if you look at the graph here for a bit, you have 15 atmosphere. So let's maintain this pressure. So roughly around this temperature, your VCM should start to boil. So you can collect VCM in the top, and then your bottom we can collect our which material, ethylene dichloride. So we are going to check what should be the reboiler temperature for that to happen, and what should be the condenser temperature in order to collect VCM as a liquid in the top, and what should be the reboiler temperature required to vaporize this particular component. Okay, so again we are going to use the same set of procedure. We will add a component splitter, and then followed by a what by the shortcut distillation column, and then we will do the regress distillation column. Okay, so I will take a break now, and then I will record after, but I will compile all the videos into one single video. So this lecture 4 or 5, I don't remember exactly, so that will be purely just the designing of a distillation column using Aspen HYSYS. Okay, so I will keep these files. So what I'm going to do is I will add I will check what should be uh, the condenser temperature, what should be the reboiler temperature in order to purify this particular stream 90. So this time we are going to get vinyl chloride monomer in the top instead of in the bottom. Okay, I will take a break now.